Good morning, everybody. We are moving on to 4.3, where we're talking about the inferences for two population means, where we assume that the standard deviations are not equal. So as opposed to what we did yesterday, where we assumed that they were approximately equal, today we're looking at where they are definitively not equal to one another. The gist of this whole process is still exactly the same as what it was from yesterday. We are introducing a new variable. It's called delta, and delta is how we find the degrees of freedom that we have to use when we go to the t-table to calculate these values. And so I'm just going to kind of skip over this first little bit because nothing there is any different than what we looked at yesterday. It's here in the red box where things are different. So we're looking at what's called the non-pooled t-statistic. And the new variable that we introduce is right here with this delta. And you can see how we compute this variable. Now, it does look very complicated just because it's a complex fraction and we've got all these variables floating around. But it's really not that bad. So I'm going to kind of try to break this down step by step. In the numerator of this complex fraction, the first item you see is the sample 1 standard deviation. So you take that sample 1 and the standard deviation and you square it, then you divide that by the size of sample 1. You do the same thing for sample 2. You take its sample standard deviation, square it, and then divide that by the size of sample 2. You'll take both those results, add them together, and then you will square that entire quantity. So once you've done that, now you can move down to the numerator of this complex fraction. And I notice an error on here that I will have corrected before these notes are posted. This term right here should be s sub 1 squared divided by n sub 1 quantity squared. So again, it's the sample 1 standard deviation divided by the size of sample 1. Square that quantity. Then you will divide that quantity by the size of sample 1 minus 1. Okay, so hold on to whatever that number is, and then you'll move over here to the other side of the denominator where you take the sample standard deviation for sample 2, square it, divide it by the size of sample 2, and then square that entire quantity. And then you will divide that quantity by the size of sample 2 minus 1, and that'll generate the second number there. So add those two together. And then once you've done that, divide your numerator by that denominator, and that will give you your value for delta. And that's the only new calculation really that we're introducing today. So it does look convoluted and complex, but really if you're just very methodical and careful about it, you will come up with the right answer. What I've noticed with some of the questions that you guys have sent me, you're setting everything up correctly, but you're getting a wrong answer. And it's not because you don't know what you're doing. It's just simply because you're making mistakes with the order of operations as you type them in on your computer or calculator, whatever technology you're using to simplify these. So the test statistic is very similar to what we saw yesterday. We have t equals x bar sub 1 minus x bar sub 2 over the square root of the sample standard deviation for population 1, quantity squared, divided by the size of sample 1, and then we repeat that with samples 2. And here's how we conduct the test. So the assumptions are still very similar. We assume we have simple random samples, that they are independent, and that they are normal populations or that they are large samples. Standard null hypothesis, mu sub 1 is equal to mu sub 2. Then you have your three alternative hypotheses, left-tailed test, or the two-tailed test, left-tailed test, and the right-tailed test, respectively, there on your screen. You compute the value of the t-statistic, and then you can move into either the critical value approach or the p-value approach. Critical value approach, we come at it initially the same way by looking at that t sub alpha over 2, or negative t sub alpha, or just t sub alpha, depending on what type of test it is. If it's two-tailed, we use the plus minus. Left-tailed, we use the negative. Right-tailed, we use the t sub alpha. The difference is we have a new way to compute our degrees of freedom, and I notice every one of these I did not put the right numerator in this term right here. So this, like I said, this will be corrected when you guys pull this up on your computers. I will fix that as soon as I get done with this video. So that's going to be the case for each one of these. So you would compute the value for the degrees of freedom, which is indicated by delta. And then you would just look at the rejection region. And then with the p-value, you look to see if the value for p is less than your significance level. Both of them are still the same. We've just introduced that new variable. So let's look at example 1, and we're going to kind of go through this whole process, and we'll be able to see how it all works. So we're talking about neurosurgeons. We're wanting to determine whether a dynamic system, which is what they called the Z plate, reduced the operative time relative to a static system, which was called the ALPS plate. The data is given on operative time in minutes for the two systems. At the 5% significance level, do the data provide sufficient evidence to conclude that the mean operative time is less with the dynamic system than with the static system? So we already know we're talking about a left-tailed test, so we need to establish our hypotheses. So our null hypothesis is going to be that mu sub 1 is equal to mu sub 2. And the dynamic plate, or the dynamic system, that's our population 1. Static system will be our population 2. So from there, we need to calculate a couple of values that are, we need to write down the alternative hypothesis. The alternative hypothesis is that mu sub 1 is less than mu sub 2, because we did indicate that this is a left-tailed test. The next thing we want to do is, I'm not going to go through the steps because these are things that we've done so many times, it should be fairly simple for you to come up with. With the dynamic system, we need to calculate the average or the mean of the values provided. So that's going to be our x bar sub 1. So we would just take all the values in the dynamic column, add them together, divide by the total quantity, and we will get that it is 394.6 minutes. I need to fix that. 394.6 minutes. We would also find the sample standard deviation for those values in the dynamic column, and we would come up with 84.7. Remember, when you're using Google Sheets to calculate these standard deviations, use the, you want to type in stdev.s so that you get a sample standard deviation. And then finally, we just look at the count of how many values there are in the dynamic column, and there are 14 values. And we'll do the exact same thing for the static column. So we first calculate the mean of the sample. So that's our x bar sub 2, which is 468.3. We calculate the sample standard deviation, which is going to be s sub 2, and we get 38.2. And the number of values in that sample is 6. So at this point, we have everything we need to conduct this hypothesis test based on the information provided. So we need to compute a couple of other things now using the formulas that we have. We also need to indicate that our alpha is 0.05. So our t statistic is x bar sub 1 minus x bar sub 2 divided by the sample standard deviation for population 1 squared divided by the size of the sample population for sample 1 plus the sample standard deviation for population 2 divided by the size of that sample. We have all those numbers, so we can put those in, and we will have 394.6 minus 468.3 divided by the square root of 84.7 squared divided by 14, and we have 38.2 squared divided by 6. When you type this in, we find that our value is approximately negative 2.861. So there's our value for t. And we'll need that when we're doing the analysis of whether to accept or reject the hypothesis. The next one, this is the new part. This is where we have to use that big convoluted formula that I typed in incorrectly several times, but I did use it correctly. So we have to calculate the degrees of freedom, which is going to be illustrated or represented by the variable delta. And for this, we have 84.7 squared divided by 14. We square that entire quantity. When we type all this in, we get a value. It's 17 point something, but in this case, whenever we're doing this, whenever we're calculating degrees of freedom, we always round down. So this is going to be approximately 17. So we have our degrees of freedom as 17. We have our t value as being negative 2.861. So now we can go ahead and do the critical value approach or the p-value approach. For the critical value approach, we have our degrees of freedom. We have our value of the t statistic. So what we want to do is we would go down on the t table. We go down to degrees of freedom being 17. And what we need to find too is, that's still the highlighter, is the t sub alpha over 2. Or negative t sub alpha rather, because this is a left-tailed test. So it's negative t sub alpha, which is negative t sub 0.05. That's our value for alpha. When we find that on the table, we go down to 17 degrees of freedom under t sub 0.05, and we find that that is positive 1.74. But because it's a left-tailed test, we would make that negative 1.740. And now we can conduct our critical value approach. Our t value is negative 2.681. So if we kind of illustrate this with a normal curve, here is negative 1.740. Anything that falls into this region on the left, we reject. Anything to the right, we accept. Our t value is negative 2.861. So it certainly falls within this rejection region. So we would reject the null hypothesis based upon the critical value approach. Let me have labeled this better. That's the critical value. And then for the p-value approach, we would take our t statistic and we want to find that probability. So we have the degrees of freedom again is 17. So this is the p-value. We have degrees of freedom being 17. We have our t value is negative 2.861. So when we go down the table and we find specifically where negative 2.861 would be located somewhere on that table at degrees of freedom being 17, we find that it would lie somewhere between 0.005 and 0.01. So that negative 2.861 lies somewhere between those two values. And our significance level that we were computing or looking at was 0.05. So it is clear that anything that lies in this range is certainly less than 0.05. So once again, we would reject the null hypothesis. And so what this tells us is that at the 5% significance level, the data does provide sufficient evidence to conclude that the mean operative time is less with the dynamic system than it is with the static system. So that's just a really quick rundown on how to do that. Again, the only thing new is how we compute the degrees of freedom, that delta variable that we introduced. The next thing that we want to do is conduct our confidence intervals and create those confidence intervals just like we have been. And so we're going to introduce that here. We have the confidence intervals for the difference between the means of two populations using independent samples. And this is called the non-pooled T-interval procedure. So again, we still have the same assumptions: simple, random, independent, normal population or large sample. We have our degrees of freedom. I still need to fix this. I'm just making myself a note. Again, I promise it will be corrected when you guys pull this up today. And then you have the endpoints of the confidence interval are going to be the difference between the sample means plus or minus whatever T sub alpha over 2 happens to be times the sample standard deviation squared divided by the sample size plus sample standard deviation of population 2 squared divided by that sample size. And we're going to do that with the data that was given in example 1. We're finding a 90% confidence interval. So with a 90% confidence interval, we have alpha is equal to 0.10. So what we have to do as far as the confidence interval goes is compute T sub alpha over 2. It would be T sub 0.10 over 2, which is T sub 0.05. And we have done this countless times. We have a specific table just for this value, but we also know that we have, I forgot to illustrate this too, degrees of freedom is 17. So what we get is 1.740, and that's the same value we found in example 1. So the endpoints are going to be the difference between the sample means. So we have 394.6 minus 468.3. Plus or minus, then we have our T sub alpha over 2 value, which is 1.740. And that's going to be multiplied by the square root of the sample standard deviation for population 1 divided by the sample size plus the sample standard deviation for population 2 squared divided by the sample size. And then when we type that in, what we end up with is we get negative 121.5 to negative 25.9. So how do we interpret that? If you look back at the notes that we looked at the other day, I gave you the 3 cases where you have both endpoints are positive, both are negative, or one is negative and one is positive. Use that where it says case 1, case 2, and case 3 to help you with these interpretations. But for this specific interpretation, we're saying that we can be 90% confident that the dynamic system compared to the relative or the static system reduces the mean operative time by somewhere between 25.9 and 121.5 minutes. And that's how you interpret these confidence intervals. Now your homework is going to be pretty straightforward as well. What I would like to see you guys do is let's do questions 1 and question 3. And the reason I want you to do those two, they both tie together. Here we're talking about, with question 1, we're talking about how much time the patient spent in the hospital bed following surgery. And I've even computed the values for you right here, so you don't have to go through and find those. And then you want to go to question 3, which goes back to everything you did on question 1, and you just find the confidence interval. So questions 1 and 3 tie directly back to examples 1 and 2 from our examples today, and that should be pretty straightforward for you. This will be due tomorrow. I got to remember what my days are. Today's Wednesday, isn't it? So it'll be tomorrow, Thursday, by midnight, and that's it. So if you guys have questions, you do know how to get a hold of me. Keep asking, keep doing this homework. Don't forget that Unit 3, all of Unit 3 is due today. From this point, starting, I guess it was Monday, we're having homework due every day now, just because you're doing 1 or 2 questions. So you guys take care. Get up with me if you need anything, and I'll be talking to you soon.